Hey, how is my favorite six block class doing today? Hopefully it's good. I know I'm having a good time on the field trip with my daughter's class. She was super excited for me to come. So I'm sorry I could not be with you. I really would like to be with you guys, as you are my favorite six block class. But couldn't make it today. So we're going to walk through another chunk of these quadratic notes. And I will be here next week where we'll really get into a lot of the repetition and practicing of applying this factoring that we're working through. But today, what we're going to do is we're going to finish answering the last couple of questions and review the first one because I know we got shorted a little bit time wise on that first question at the end of class on Wednesday. So, what were we talking about? Well, guys, we were factoring a very special kind of polynomial called a quadratic polynomial, right? You never skip leg days with a quadratic. And what we talked about was that our method of factoring polynomials, which works for almost all polynomials, divide by a factor to get a factor and put it together, won't work for a quadratic because most quadratics' greatest common factor is going to be 1. And even if it's not 1, it's just another number like 3 or 5 or something, it still isn't going to get us a fully factored form. The best it can do is get us a partially factored form, which is not what we're going for. So we started to talk about, okay, so how do we going to do this? What is the new factoring process that we have to work with for quadratics if divide by a factor to get a factor and put them together isn't going to work? And what we discussed was working through 4 questions that would help us unpack this factoring process for quadratics. And the first question, which we answered in class on Wednesday, was what does a factored quadratic polynomial look like? One of the things that makes the quadratic special is that its factored form will look the same always and forever from the day math was discovered till the day the sun explodes and destroys all life as we know it. All right. And we discussed that form is a binomial times a binomial, where the first term in each binomial is a variable of x to the first, and the second is a constant. And we discovered that by distributing, simplifying, right, these binomials and realizing that the outcome of our simplification was the simplified form of a quadratic. So logically, if the end of our process was a simplified quadratic truck, and we work backwards, the beginning of our process had to be a factored quadratic robot, right? So we left off that first question by saying our factored quadratic is always going to look like a binomial times a binomial, where the first term will be x with some coefficient, some number times x plus a constant plus some number, right? And that's great. That helps us get started. That gives us a place to begin working. But the real question is we've got to be able to fill in those blanks. Each of these rectangles and these blanks here have to be filled in with a specific number so that the factors will actually match with the simplified terms in our trinomial. So to answer that, we started with our second question here, which is how do we find the variable terms in each binomial factor, right? And so we did this little exercise. And again, we didn't get to do this in full on Wednesday because we're running short on time. But hopefully what we remember is that we were able to match the factored quadratic robots with the simplified quadratic trucks by comparing the distribution of the variable terms in the binomials, so x times x, 2x times x, 3x times 2x, with the leading term of our simplified quadratics. And what the conclusion we came to was that the multiplication, the distribution of the variable terms of the factors over here will always equal the leading term, the first term, the x squared term of our simplified quadratic truck. All right, and that is what we kind of wrote down right here, that the variable terms, the x terms in the binomial factors will always multiply to the leading term. Again, this is another 100% straight facts, always going to be true. That will always happen. And we didn't really get to do this exercise here at the end of if we knew the leading term was 20x squared, what could possibly be the terms in the factors. In other words, what could go here and here that if I multiplied them, I would get 20x squared. And this is where we definitely ran out of time. There are actually 6 different possible factor pairs that could multiply to 20x squared. And you can see right here, 20x times x, 2x times 10x, 4x times 5x, and their negative counterparts there, right? And so while that gets us down the road, right, eventually the question is going to be, and we're going to come back to this, how do we know which of those 6 pairs of factors is the right one to choose from? But put a pin in that for now. All right, because we're moving on to our next question here, which is not how do we find the variable terms, we just answered that, but how do we find the constant terms, right? If it's a binomial, it does no good to only know one of the 2 terms in a binomial. We got to know both of them. All right, so here's what I want you to do. I'm going to pause the video in a second, and I just want you to look at the factored robots. These are factored quadratic robots over here, and these are simplified C-value blanks. So notice it's not the whole quadratic trinomial, but just the last term, the C-value. And without doing any work, right, other than maybe pushing buttons in a calculator, you're allowed to do that. But without doing any work, I want you to try and figure out what the C-value for each of these 6 factored robots would be in comparing them. All right, so see if you can figure out how to do that, and pause the video now. Welcome back. Well, hopefully you got the same C values that I did, the same constants that I did there on the right. And what I hope you recognized is that the C value, the constant value in the simplified quadratic, is always going to come from the constant terms being distributed in the factors and the binomials. So the -6 times 7, the -13 times 4, the -4 times -8 is always going to produce that C value in our simplified quadratics there. So again, what does that do? Well, that gives us another piece of this puzzle, right? Because I now know how the variable terms in the binomials connect to the simplified quadratic. That's the leading term. And we also know how the constants connect to the simplified quadratic, which is the constant term. That's nice. Constant times constant gives you a constant, right? Pretty straightforward there. So you can see in this kind of graphic right here that in the simplified binomials, guys, whenever you multiply the constant here times the constant here, you should always get the constant in your simplified quadratic truck. All right? So that's what we're saying there. And that's always, again, these are always things that are going to be 100% factually true that we can use to get these factors, rather than getting them chronologically as we do and divide by a factor to get a factor and put them together, where we're getting one and then getting the other afterwards. Again, this is how we're going to be able to get both factors simultaneously. So here's what I would like you to do, again, to pause the video and try and come up with all the different possible constants that could go in the binomials here, to that if we distributed them, we would end up with -28. In other words, what could you put here and here? Give me terms, constants that could go in those blanks that could multiply, that when I distributed them would give me a constant simplified term of -28. And I want you to come up with as many as you can think of there. All right, so pause the video and try that now. Welcome back. Let's see how we did. So we should have come up with 6 unique factor pairs that could multiply to -28. -1 times 28, vice versa, -2 times 14, -4 times 7, and those opposites there. And again, this leads us to a question. Well, if there's 6 different possible pairs of numbers that could work in these factors, how do we know which one is correct? And if we put those 2 questions together, if the leading term was 20x squared and the constant term was -28, there's 6 possible ways the variable terms could work, and there's 6 possible ways the constant terms can work. How do we pick the right pair for each? And that brings us, guys, to our last question here, which is if the leading term and the constant term both work, How do we know which one is correct? And so take a look at these examples down below here, which I'm going to have you go through in a second here. Just look at row A. Just going to look at row A real quick here. We have a simplified polynomial ax squared plus 8x plus 12, which is the same in all three of these equations. But notice I have different binomial factors in each of these. Well, only one of these equations is true. Only one of these equations is actually the correct binomial factors for the simplified quadratic. Only one robot matches its truck, is what I'm saying here. And guys, the way we can figure this out can't be from the variables or the constant terms alone, because look, in all three of these, x times x gives us x squared. So the x times x, x times x, x times x, they all work out. Notice the constant of 12 in our simplified quadratic would work for all of the constants in the binomials. 6 times 2 is 12. 4 times 3 is 12. 12 times 1 is 12. So there must be another way for us to figure out which of these factored forms is the correct outcome for the simplified quadratic. And that's what I want you to do, is to go through each of these 5 lists. And in each of these 5 lists, A, B, C, D, and E, one equation is correct and 2 are wrong. All right. And so I just want you to investigate and figure out in each of these 3 choices where you can see the trinomial is the same every time, how can you figure out which factors are correct when, again, you'll notice this in all of them, the variables times the variables give you the right leading term, right? 5x squared works out. And the constant times the constant gives you the correct constant term, last term, 8. So how do you know which of those is the correct one for 5x squared minus 22x plus 8? So I want you to investigate that, try some things, see what you can come up with. Pause the video now. Welcome back. Well, did you find the same pattern that I did going through these 5 different lists? So in A, it was the first equation. In the B, it was the middle equation. In C, it was the last equation. In D, it was back to the middle. And then in E, it was the last equation again. You can see my work in green for the ones that were true, and my work is in red for the ones that didn't work. Well, what conclusion can we draw from this? How can we tell which pair of factors is correct when the factors correctly match, for all of them, the wrong ones included, the leading term and the constant term? And hopefully what you realized is we've got to check the middle, right? If the first and the last all work out, it's the middle that's going to tell us which one is actually correct. And what you'll notice is not distributing variable to variable or constant to constant, but distributing the outsides, right? So if you look at A, we distributed the x to the 2. Those are the outside terms. And the 6 to the x, the inside terms. So outside distribution and inside distribution added together gave us the correct middle term there. Whereas you could see in the example, sorry, just trying to get that lined up there perfectly. In this example down here, when I distributed x times 6 and 7 times x outside and inside and added them together, I got positive 13, but in my simplified quadratic, I needed a negative 13. So I knew that those factors, that's not the right robot for that truck. Those are not the right factors for the simplified quadratic there. And if you go through each of these, you can see the ones in green, the 2 distributions added together, where we were distributing a variable to a constant, the outsides and the insides matched the middle term. And that, guys, is exactly what we are looking at here when we're trying to check factors that seem to work out for the leading term and the last term, the constant term, but that's that middle term that's gonna make it bona fide or not. That's really gonna let us know whether these factors are lying to us, whether they're posers, or whether they're legit, they're the real deal. All right, so the outside plus inside. So you can see taking the variable term in the first binomial times the constant in the second, and the constant in the first times the variable in the second, outside plus inside has to equal that middle term. All right, so These 4 questions all put together, what does the form of our robot look like? How do we determine the variable terms in those binomial factors? How do we determine the constant terms in those factors? And then if we've got the first term and the last terms taken care of, how do we check it to make sure it matches the middle term in that simplified quadratic? Those 4 questions together give us a specific way to think through what we call educated guess and check, because that's what we are really going to be doing to simultaneously create the binomial factors. And the acronym I like to use for that is VOICE. Yes, use your voice. We will be the voice when we are factoring quadratics. All right, well, how does this voice work? Well, let me drag this up. Sorry, I didn't get this in there ahead of time. Well, guys, if you look at the 3 terms in the simplified, ax squared and c, what that creates for us is an educated guess by making sure that the variable distribution and the constant distribution match ax squared and c. What we now have is an educated guess. All right, but as we saw in the previous question, just because ax squared, the leading term, and the constant work out doesn't mean the binomial factors are correct. So what we need is a way to check our guess, and that is with the outside plus the inside, right? And that has to match the bx term. So this right here, guys, is how we are, just a little bit off there. Let me get that lined up for you. Perfect. There we go. All right. And that is how we think through the acronym VOICE. Now, I want to be very clear. VOICE is just a mnemonic device to remember this educated guess and check. If you don't like it, you don't have to use it. But that is what I'll be using and kind of modeling and everything. Plus, I got a fun music video that I'll share with you at the end here. All right. So VOICE, V, the distribution of the variable terms, V, always has to give you ax squared. O plus I, the outside and inside distributions added together have to give you the middle term. And C, the distribution of the constants from the binomials, has to give you the constant term in our simplified. And if V, O, I, and C all check out, then you know your factors are equal to the simplified quadratic you started with, E equal. So this, come on. Oh, nope, don't want to do that. Sorry, give me a second here. All right, this... Come on, there we go. This is what that will look like. And you can see if you write V, O plus I, C, and E across your simplified quadratic truck there, it spells out the word voice. And then if you can match the 4 distributions of the factors, of the terms of the factors, the binomial factors, to those letters, you can clearly see the connections that have to be made between the factors and the simplified voice. All right, so let's give that a shot and try and put that into practice here. All right, so I will color coordinate all of these better. And what I will also do in these examples here, guys, in 1 through 6 is to show you both a good guess that works out, but also before that, a guess that doesn't work out. So you can see the idea that your first guess might not be correct, and you just got to play around with the numbers, try some different combinations, and figure it out. So if we look at this here, what do we know? Well, I know that if I multiply this x term by this x term, it has to equal x squared. All right? And that is, just to be clear, guys, 1x squared. So what numbers could go in those rectangles to give me 1x squared? Well, hopefully, guys, you figured that out pretty obviously. 1 times 1. And when your a value equals 1, guys, the ninja, that's going to be the easiest factoring we can do. So that's kind of what you're hoping for. You're hoping for an a value of 1. That makes your guessing the easiest possible. All right? But then what do we know? I know that whatever goes here and here, the constants in my binomials have to equal negative 22. Okay, well, what are 2 numbers that can multiply to negative 22? Just off the top of my head, let's take the easiest possible pair. Let's go with negative 22 times 1. All right, so what we have right now is we have variable terms and constant terms right here in my variable terms right here and constant terms right here that will match the leading term right here and the constant term over here, right? The question is, are they the correct ones? Well, last but not least, remember this, we've made an educated guess. Now we have to check it. So 1x times 1 gives me 1x. Negative 22, so that's my outside. Negative 22 times 1 is negative 22x. That's my inside. And if we add those together, I get negative 21x. The problem, guys, is if we have the right factors, that should add to negative 9x. So here's the deal, guys. That is incorrect. That is not the right factors. So you know what I have to do? I have to erase all of this and try again, right? Erase all of that and try again until I find the right values to work out to give me the right values in my binomial factors that will distribute to give me the right terms in my factored form. All right, so if we try this again real quick here, and again, I'll map this all out for you nice and neat in a second when we come back. We still need 1 and 1, but I don't know. Let's just maybe try negative 11 and positive 2, right? Those are numbers that will also multiply to negative 22. So what are we going to do here? So now let's check it. 2x plus negative 11x. Oh, and there we go. Look at that. We got negative 9x, and that is exactly what we were looking for. So what do we know the factored form of x squared minus 9x minus 22 is? We know it's going to be x minus 11 times x plus 2. And that is the correct pair of binomial factors. All right, the more you practice this, guys, the better you're going to get at it. So here's what I want you to do. We're just doing the 6 problems on this page. Don't worry about the next page. But what I want you to do is try to guess and check, thinking through the acronym VOICE, thinking through your binomial factors there, and see if we can get 1 through 6 there. All right, so pause the video and give those a shot now. Welcome back one final time here. How did we do on these? So here's the first 4 you can see in the video. We already did number 1 together. Here's number 2, x minus 10 times x minus 4. Here's 3 and 4, x plus 7 times x plus 3, and x plus 12 times x minus 4. Now, if you notice, the one thing that 1, 2, 3, and 4 all had in common was the a value, the leading coefficient, was 1. Which meant the variable terms in the binomials were also just 1x and 1x. Down here in 5 and 6, things you might have noticed got a little bit more complicated in terms of guessing correctly, maybe right off the bat, because now our leading coefficient was 2 in problem 5, and in problem 6, the leading coefficient there was 3. But guys, it doesn't matter what the a value is. The process is the same, right? Make sure you've got variable terms that give you the ax squared. Make sure you've got constant terms in the binomials that give you c. And then that's a plausible guess. And then use the outside plus inside distributions to check the middle term b. Use your voice, be the voice. And if you've been wondering, why does he keep saying those things about the voice? Well, just listen to this.
What the hell? Was that because of us? I don't know. I mean, it started off super positive, then it just got crazy.
I did not like that at all.
No, Kev. None of us did.
Yeah, it was totally messed up. It's disgusting how people will just, take something good and just take advantage of a situation.
Yeah.
There was no time to do anything except just leave and just hope that you're not hurt.
It's great to have you guys back, by the way.
Well, thank you, man. Feels good to be back.
See you, man.